Good morning, physics class. Wanted to say hello and get you guys ready. We are 5 weeks till the end of the semester here, I believe. So I wanted to check in on you, make sure you're doing all right. If you need anything, let me know. But I wanted to give a couple minutes of review over what we've been doing the last couple of weeks. And also encourage you to please keep it up for fourth period. That's that long period that I had with you guys. I've only got 50% of people turning in assignments. So those of you who are not doing it, please make an effort. Please try, because assuming you're able to pass my course, you should have learned the physics you need to go into something like pre-AP physics or AP physics, or to be prepared for taking physics classes in college if you should want or need to. So please make sure you're putting that effort in, and you can do this. I know it's a little bit tough at home, but do your best. So as for what we were going to review, let's see if I can move this much. We had been talking about series circuits and parallel circuits. Notice that for a circuit in series, the electrical current will flow through one resistor, then the other, back to where it started, and it'll keep going in that loop, traveling successively or in series 1, 2, and 3. For that one, you calculate the resistance for the whole circuit, right? We saw how to do that. We saw the formula to do that. R total equals R1 plus R2 plus R3. You'll use that to calculate the current using Ohm's law. I equals V over R. You'll calculate the voltage for each resistor. Remember that the voltage will be different at each location based on its resistance and the amperage, because the amperage is going to be consistent all the way through, or constant all the way through. And then you'll check to make sure that each of these little bits of voltage drop adds up to whatever your voltage was that you were starting with. For parallel circuits, you've got electricity moving through a wire, and then it splits and goes two ways at once. This is like a river that splits in two, and part of it goes through one, and at the same time, a different part of it goes through another resistor, and then they'll meet back up and go back to where they started and flow through again. So they're flowing through these two resistors in parallel, or at the same time. For these ones, you'll calculate the total resistance of the circuit. This is the more complicated one. It's 1 over R total equals 1 over R1 plus 1 over R2, etc., for how many you have. You'll calculate the current just as you did before, just making sure you do your algebra correctly. You'll calculate your amperage at each resistor. Remember that the voltage is the same everywhere, but the amperage is what's changing on this one. So you might have different amperage here than amperage here. Then finally check your work to make sure it all adds up. So as a reminder, when you're working with this, for a circuit in series, amperage will be constant throughout, but voltage drops are different depending on the resistance of the components. But in a circuit in parallel, voltage drop will be constant throughout, but amperage will be different based on the resistance of the components. Pause this as you need to solidify your understanding. Why is that the case? Well, I think it's easier to start with in parallel. In parallel, there's less resistance in general because that current is splitting up. So the current is going to flow more easily, giving us the same amperage throughout, but different voltages. But in series, the total resistance makes the current flow at a constant rate. There's the same amperage, but the electromotive force, called voltage or potential difference, is consumed across each resistor and varies depending on the strength of that resistor. So these are like dams in the flow, and that voltage is being blocked successively. All right, let's talk about... Oh, it didn't come up. I'm going to pause and go get it. So last, let's talk about lenses that we've been doing for the last week. Let's see where I can put this where it won't be in the way for you. So you should have seen in your lab last week, and you're going to do a little bit of practice on this week. So take notes as you need to, pause as you need to, make sure you've got these notes. if you have an object at twice the focal length, this is some distance, this is double that distance from the lens, it's going to produce a real image over here. Let me see if this comes up. There it is. This is real because this image can be projected onto a screen like a movie projector, or like my glasses project an image onto my retina. That image is inverted, or like your cornea and lens projects a lens on an image onto your cornea. It's real because it can be projected, and it's on the opposite side of the lens. Inverted, meaning it's upside down from what it was before. And at 2f is a special case, meaning or where the object is the exact same size. And hopefully you were able to see this in your lab last week. Objects that are at the focal length focus at infinity. Okay, this is useful for lighthouses and searchlights. And an object at infinity will focus at the focal length prime. That's why it's called the focal length. That's where the energy is focused. This is useful for burning holes with magnifying glasses or a magnifying lens. An object that is between the lens and the focal length will produce a virtual image. This is our only case in which we have a virtual image. It's upright, and it's virtual because you can't project it onto a screen. Okay. But it's upright and it's magnified. It's going to be bigger than it was otherwise. An object outside of 2f will create an image between f prime and 2f prime. So if this is some distance, the focal length, then between one focal length and two focal length, you'll have the image. It will be smaller, as you see here. It'll be upside down. And it will be real because you can put this on a screen. All the rest of these are real images. Vice versa, if you've got an object between the focal length and double the focal length, it's going to focus somewhere outside of twice the focal length. This object will be bigger, it will be upside down, and it will be real because you're putting that, you can put it on a screen. This is how movie projectors work. I got a little projector over here. It shines an image, about this big, but when it moves all the way across the movie theater, it's as big as a movie screen. So that's because we've got the image between F and 2F, and we're focusing on it on a screen that's farther out there, and it's much magnified, much larger. Now that means that they run that movie upside down in the screen. In the projector, and then on the screen it goes right side up. Okay, so that's a little review of how lenses work. Good luck with your assignments for this week. You'll see them on the stream. Thanks, y'all. Let me know if you need anything.